All right, everybody, welcome to Module 8, where we are going to be introducing our second form of hypothesis testing, what are called single sample t-tests. So, before getting into the specifics here, again, the last module was all about hypothesis testing in general and the process of that, and we learned probably the simplest type of hypothesis test, which is a z-test. So, we're going to be using that same 5-step framework, but we're going to be applying it to different contexts. You might have noticed that in the z-test, we actually knew both kind of population parameters we were interested in. The mean of the population we were comparing our sample to, and the standard deviation. Most of the time in real research, we don't know either of those things. We don't have that information. Remember, parameters are very hard to estimate. So these single sample t-tests will help us address one of those common situations. Additionally, again, we try to be transparent about what you'll be assessed on. I'm going to go ahead and tell you that as we accumulate more of these hypothesis tests, a question type that will be on every single exam from here on out is that I'm going to be describing different types of research to you, and I'm going to be asking, hey, what's the right hypothesis test to run, and how do you know? On this upcoming exam 2, that's going to cover modules 5 through 8, there's only going to be two possible options, the z-test and this single sample t-test we're introducing now. Eventually, it's going to be more like 7 or 8. So you're going to want to keep track of these decision rules that help you figure out when to run one test versus the other. So here's how it works. Again, we ran that z-test when we had a mean of a sample, and we wanted to compare it against a population where we knew both the mean and the standard deviation. But in reality, you almost never know all of that information about a population. A lot of times we can estimate mu, sometimes we actually know what mu is, but oftentimes we have no information on standard deviation, on those measures of variability. So here's our first decision rule. Both the single sample t-test and the z-test are what are called one sample tests. That's where you have one sample of scores that you're actually measuring, and you're comparing it to a population that you know some stuff about. Here, what distinguishes between the two tests is what we do and don't know about those populations. So specifically, we run a z-test when we know both of our parameters. So if we know both the population mean and the population standard deviation, we would run a z-test. If we know the mean, but not sigma, if we know the mean but not the standard deviation of that population, we run a single sample t-test. So here's your first decision rule. If you are comparing one sample of scores to a population that you know some information about, if you know the standard deviation of that population, you would run a z-test. If you do not know it, you would run a single sample t-test. So let's look at what some examples of this might look like. Let's say we didn't know the population standard deviation, but we did have an established baseline, some kind of a basis of comparison. So we have a mean that we can compare our sample to, but we do not know anything about the variability. A pretty common approach, a lot of times we assess things by comparing them to a chance standard. So for example, a common way of testing how good people are at detecting lying is you show them a series of statements people are making. Half of them are true, half of them are lies, and they have to try to assess which is which. Here's the thing about that. You can't just measure how many they get right, because if they just flipped a coin or used pure random chance, you'd expect them to get about half of their guesses right. Half are lying, half are telling the truth. If you guess every single time, you're going to get about 50% of your guesses right. So we have to compare it to that baseline, our chance standard. If we just purely guess, the mean correct responses would be 50%, but we have no idea what the variability would be. Or let's say we want to measure the heart rate for frequent coffee drinkers. I got a little right over here, so I can sympathize. So frequent coffee drinkers relative to average people. Let's say that we know the average heart rate for the population, for just people overall, but we don't know any information on how much variability that has. In that case, we couldn't run a z-test because, again, we're missing that population standard deviation, that sigma. Also, these sort of tests can sometimes involve small samples, relatively few people in a sample size. The sample size thing is mostly moot for this course because we use data sets that are really simple by design. There aren't many people in them. But in reality, how many people are in your sample has a pretty dramatic effect on the predictions you can make. Remember, for that sampling distribution to become a normal curve, you need at least 30 people. And realistically, you need at least 30 people per condition. The t-test was designed to deal with those sort of situations. So the t-test is a family of tests. There are 3 of them. We're going to learn the other 2 in the next module. But here we're dealing with that single sample case. So t-tests are used when we know the mean of the population we're comparing our sample to, or at least can estimate it very quickly, but we don't know the variance or standard deviation or standard error of that population. Little history lesson and why you saw like an old Guinness ad on that title slide. The t-test used to be called the student's t because the individual who came up with the t-test, William Gossett, he worked at the Guinness brewery here and actually devised these tests to measure things like chemical composition of small batches of beer. He wasn't allowed to publicly talk about his work, so he published it anonymously under the pseudonym Student. So if you see an old stats textbook, they'll sometimes call this a student's t, but we've dropped the author and it's just a t-test now. Anyway, again, the simplest case of a t-test is one sample compared to a population mean that we know or can easily estimate, but the variance is unknown. We're going to have to figure out how to get that variance. So when might we use it? We might check a sample versus an advertised claim. Remember we mentioned that Doritos example? Additionally, some student researchers have done things like they go to Subway. Subway has the foot-long sandwich. They measure a bunch of the different buns there, a sample of them. They know that the population mean is supposed to be 12 inches. They don't know the variability. What they found was, unsurprisingly, it's more like an 11.5-inch long sub, a little bit shorter than they're saying. Similar things with like Oreos and double stuffed cookies. A group of students said, okay, this should have double the stuff and twice the filling of a regular Oreo, and measured it and found that it was closer to like 1.7 or something like that. They were able to reject the null and find that Oreo is not giving you double the stuff. We also can compare a sample to a known norm. A lot of standardized tests will have population means that are established, but may not have measurements on variability. Or again, what we already mentioned, we compare behavior to a chance standard, something that's based in probability. What would happen if you guessed every time? That can sort of form our population mean, but we don't know the variability. But remember, again, these t-tests, especially the single sample t-test, they're used when we do not know that sigma, the population standard deviation. That's what helps you determine when to choose one versus the other. And again, you are going to get those questions on the exam. So definitely get that one sort of embedded deeply in the part of your brain that's going to take the test. Single sample t-tests are about the simplest example of a test you might actually run as a researcher. Z-tests, again, what we learned before, they can happen, but they're pretty uncommon. They're pretty uncommon and usually can only test pretty straightforward relationships. So you might run a z-test as a real researcher, but it's more likely this would be about the most basic test you would run. So that's why we start here in talking about those t-tests overall. So here's a review of our 5 steps, but we will talk about what changes in each step. Step 1, identifying our hypotheses, does not change. Step 2, determining the characteristics of the comparison distribution. We now know the population mean. We don't know the population standard deviation. Another factor, our third characteristic, the shape of that distribution, is actually going to change a little bit. We'll account for that in a couple of videos. Find the critical value. That doesn't change. Again, we set the alpha. We find the critical value. Some of the specific critical values will be a little different because the distribution is shaped a little differently. But for our purposes, for your purposes, it's still just you're being given these critical values. You're copying them down. Step 4 is figure out our test statistic, determine where our sample score falls, and we use, again, t-scores instead of z-scores in this case, but the formula is going to look really similar. And then we make a decision on whether to reject the null. Again, that is a binary decision. You're either going to reject the null or not. It's based on that same comparison. Compare your test statistic to your critical value. If it's beyond the critical value, reject the null. If it's not, fail to reject the null. And that's it. We're going to start up with the next video and talk a little bit about one of the big hurdles of these t-tests, which is how do we estimate this parameter that we had on our z-tests that we no longer have, the population standard deviation. To be continued.